Hello learners, in this section we are going to learn about the index of goodness of fit for multiple linear regression. The index of goodness of fit for multiple linear regression is the coefficient of multiple determination. The same concept of the coefficient of determination can be extended for a multivariate model. Coefficient of multiple determination is denoted by capital R square. It is a number that determines the proportion of total variation in y, which is explained by the independent variable of the regression line. Coefficient of multiple determination is defined as R square equal to explained variation divided by total variation equals to SSR by SST, where SSR is the regression sum of squares and SST is the total sum of squares. We know the relationship of three measures of variation is SST equals to SSR plus SSE. Now using this relationship, we can get that R square equal to 1 minus SSE by SST, where SSE equals to error sum of squares. We can also the expression for R square like this, which are just the expressions of SSE and SST. The value of R square lies between 0 and 1. The greater value of R square implies better fitting of the model to the data. In general, R square increases when an independent variable is added to the model, regardless of the value of the contribution of that variable. Therefore, it is difficult to judge whether an increase in R square is really telling us anything important. So, it is preferred to use adjusted R square. Adjusted R square is the coefficient of multiple determination adjusted for degrees of freedom. The expression for adjusted R square is R square equals to 1 minus SSE divided by n minus p. And this expression is divided by SST divided by n minus 1. Here n minus p and n minus 1 are the degrees of freedom. So after some algebraic manipulation, we can establish a relationship between adjusted R square and R square. And the relationship between adjusted R square and R square is R a square, which is adjusted R square, equals to 1 minus n minus 1 divided by n minus p into 1 minus R square. Here n is the total number of observations and p is the number of independent variables. Since SSE by n minus p is the residual mean square and SST by n minus 1 is the constant, regardless of how many variables are in the model, adjusted R square will only increase on adding a variable to the model if the addition of variable reduces the residual mean square. Adjusted R square increases only for potential independent variable, but R square increases for all variables. So, sometimes R square may give us misleading conclusion. For an important or potential independent variable, both R square and adjusted R square will increase, but for an unimportant independent variable, R square will increase, but adjusted R square will decrease or increase negatively. Degrees of freedom plays an important role in small samples. So, when sample size is small, and when the difference between R square and adjusted R square is large, we will use adjusted R square. Adjusted R square is always smaller than R square, as after adding an independent variable, SSE will decrease, hence R square will increase. Besides, adjusted R square will increase if the independent variable reduces the full term SSE by n minus p. When R square equals to 0, then adjusted R square equals to 1 minus p divided by n minus p. When R square equals to 1, then adjusted R square equals to 1. We know that R square lies between 0 and 1, and the range of adjusted R square is this, which is 1 minus p by n minus p less than equal adjusted R square less than 1.